Okay, can you hear me? Thank you for replying. So I think it's fine. So actually in the previous class, my mic was broken. So I replaced this mic. Okay, I think it's working well. Okay, great to see you everyone through the Zoom. Even though this is the Zoom classroom, but I can see your faces. So that's good. So okay, in the previous class was the introductory class. So I introduced about this course. This is the computer architecture course. So yeah, this is the mandatory course in Department of Computer Engineering and Science. So so I think every student who wants to major in this area need to take this course. So actually, if you enter the Department of Computer Engineering or Computer Science, so you may think that, oh, we need to learn about the computer software and how to program, and then how to write the actually programs. But in the computer engineering, so we need to learn about every aspect of computer research, not computer programming or some how to program either Python or C. So we need to learn how computer works and then how to generate the efficient computer software or computer programs. Also, the computer is composed of many components such as simply hardware and software, but actually the computer is composed of various layers, and then that means the very large amount. So it's a various components, including software and hardware. So we need to learn how to manage or how to build or how to generate these computer systems. So in this course, we will learn about the computer systems or computer hardware architecture. So especially, we will learn how the computer systems works, okay? So these are the computer systems. Okay, I believe, so we learned until this slide. So okay, we learned that these are all computers. So actually in the current recently we use computer systems or computer hardware every time and everywhere. See, it is because, so actually this is the mobile computing era. So that means we actually we use our smartphone or a smartwatch or even the smart speakers. So these are all computers. Also, so computer hardware is advancing. So actually traditionally, these are some conventional shape of the computer systems, but the computer systems are also advancing. So we are applying some various type of computer processors or computer hardware in our computer systems. So for example, we are using GPU. GPU means the graphics processing unit. So actually we use this GPU for better gaming environment, but recently we use GPUs for parallel applications, especially machine learning applications. So these are some specific hardware that accelerate the performance of computer systems. Also, a cloud computer system, where cloud infrastructure and server computer systems are the kind of computer system. Okay, so we are using computer every time. So actually the computer hardware has various figures. So then its computer hardwares are designed for its specific purposes. So that means if we build the personal computer system, we just focused on the performance. So the performance means that how can we run our program faster? Then also cost. So actually we want the cheaper computer system or a cheaper smartphone or a cheaper laptops. So for the personal computer systems, cost and performance are important, but we trade off these cost and performance for our personal computer systems. But how about the server computer system? So for the server or cloud infrastructure, many users, actually the large amount of users connect to the cloud computer systems or server computer system, and then they learn their own software or their own applications. So that means the server computer requires the very high performance. Also, the server computer systems require very high capacity on memory capacity or storage capacity. Okay, so that's the design goal of the server computer systems. So mobile, so energy efficiency is very critical because mobile computers run using batteries. Okay, so just it's just very funny quiz, like which computer or which processor is better. So actually, so after taking this course, you need to answer these type of questions. So which processor is better, like Intel Pentium or ARM processors, Xeon and i7, Xeon and NVIDIA GPUs, like NVIDIA Tesla or NVIDIA Ampere. Okay. So, okay, let's start today's class. So let's just focus on the performance of computer systems. So what is the performance? So usually performance means the speed. So we frequently say, oh, this computer is faster than that computer. So we just focus on faster, right? So faster means that the computer runs. So these better computers learns the same program or same software within shorter time. That means the speed, or that means the performance of a computer system. So it's a time, actually. In the computer engineering terminology, that means the latency. Okay. So everyone wants faster computers. And that's obvious, right? We want to buy faster computer with the same money. Okay. Then which factor determines this performance of computer systems? So faster means that our program runs on the computer systems, and then this program complete faster than other computer system. Okay, so the interface is change. Okay, let's see which factor determines the speed or the performance of a computer system. The first factor is the algorithm. So what is the algorithm? So algorithm is,
잘 모르겠네.
sorry, someone is talking. So if you want to answer, then please turn on your microphone, and if not, please turn off your microphone. Okay. So algorithm is some methodology to solve the problem. So we can apply the various algorithms. So for example, let's assume that we are computing matrix multiplication, like matrix A multiplied by matrix B. So actually this is easy and this is very simple, but we can apply various types of algorithm for this computation. So actually the answers are the same, right? So if we perform the A multiplied by B, then answer should be C, and then this answer should be correct, okay? But we can apply the various types of algorithms. So we can apply some best algorithms, so we can apply some more efficient algorithm for this matrix multiplication. So algorithm is the software part, right? So if we write the program for computing matrix multiplication, then we just generate our own program, okay? So this algorithm is the software part, okay? So algorithm determines the number of operations. What is the operation? So something like additions, multiplications, and something like that. Those are the operations. And then another factor is the programming language, compiler, and architecture. So architecture means instruction set architecture, such as the x86 or ARM. So x86 architectures are frequently used for our personal computer systems or server computers like laptop. And then ARM architectures are frequently used for smartphones or mobile computer systems, okay? So what is the program language? Such as C or Python. Okay? Which language is faster? So C is much faster than Python language because some type of language is different. The Python is the interpreter language, and then C is the compiler language. So C is, if you write the same program with the C and Python, then C program will be much faster than the program written in Python. Okay, so program language also decides the performance of a computer system. And then compiler. So I mentioned the compiler when I mentioned C language. So actually the C language is very similar to our normal language, that means English. So this type of language is called the high level language, okay? Because these high level languages are very similar to our normal language. But computer hardware cannot understand our normal languages, okay? So this high level language should be translated into the machine language or machine code. So this compiler is very similar to the translator, which translates the high level language into machine language. So the compiler also determines the performance because it's the same program, and then this is the compiler A, and then compiler B. Compiler A can generate the more instructions. So more instructions are very similar to the more operations. And the compiler B may generate the less instructions. So which is faster? This one will be faster. But we don't know actually. But usually this compiler will be faster. So program language, compiler, and instruction set architecture also decides the performance. So this part and this part is the kind of software, and then architecture. Architecture is the interface between software and hardware. Okay. 3. Processor and memory systems. These are hardware. So we can apply the i7, i5, i3 for our laptop. So which processor is faster? i7 is the fastest CPU among these 3 CPUs. Right. So processor, that is the hardware, also determines the performance. And the memory system, so we can equip 16 gigabyte, 8 gigabyte, and the 4 gigabyte, 2 gigabyte. So if we invest the more memory, so then the larger memory in our computer system, then we expect that the performance of this computer will be faster. Okay, the hardware. And then I/O system, including operating systems. So I/O means is the input and output devices. So in the computer system, so what are the input and output devices?
Keyboard.
Yeah, keyboard, mouse, mic. And then also I'm using a microphone. So this is also kind of input devices. And then network like Wi-Fi or 5G and then LTE, 4G. So these are also I/O devices or I/O. So input and output. And then these I/O devices are also managed by operating systems. So I/O devices, I/O systems are also I/O systems decides the performance of a computer system. So there are many factors: software like algorithm, and the program language, compiler, and the computer hardware like processor and memory, and then input and output systems. So all these components decides the performance of a computer system. So I said, so if you study the computer engineering or computer science, then you are working for better computer systems or better computer hardware or software. And then I said that a better computer hardware or better computer system means the faster. And then this performance is determined by many factors. So that means the various area of the research in computer engineering. Okay. So that's why we need to learn about these computer systems or computer hardware and computer architecture. Okay. So we need to learn. So we need to understand the basic of computer hardware or computer systems. For better computer system, like so in the previous slide, I just focused on the performance. Okay, but not and then another important factor of our system or engineering is the cost. So we need to minimize the cost, like energy cost or some labor cost, also the area. Those are all cost in our system. So, and then this type of knowledge is also required for software engineer, not only the hardware engineer. Okay, because as I mentioned, these all factors decide the performance of computer system. Computer system include software and hardware. And then our goal to learn computer engineering or computer science is to build up these better computer systems or better computer hardware or better computer software. And then for this purpose, we need to learn this about the computer systems. For better software design, then recently the computer systems are advancing. So that means the computer hardware is changing. So for example, we need to use the GPU for better machine learning systems or better neural network applications, right? And then in order to learn our machine learning or neural network applications faster, then we need to understand how GPU works. And the GPU is the hardware, like domain-specific software. And then also hardware and software co-design is also very important because computer systems are composed of hardware and software parts. Okay? So it's very critical, it's very important. So that's why this course is a mandatory course in computer engineering department. Okay. Okay. So what did you learn in this course? 1, 2, 3, 4. So actually, I mentioned these factors or these items in the previous class, like instructions architecture, compiler performance, and then pipeline design, and the memory, something like that. So we learn about this hardware aspect of the computer systems and hardware and software interface. Okay, do you have any questions? So if you want to ask questions, you can use the chatting window. Also, you can turn on your microphone and then you can you can ask questions via your Zoom microphone, okay? And you can speak in Korean if you are, okay? Okay, let's move on. Okay. Let's talk about the abstraction of computer systems. So actually in the previous class, I also mentioned abstraction. So what is the abstraction? Abstraction is simplified view. And then actually, simply speaking, abstraction means, so yeah, so for doing something, I want to learn the minimized knowledge, so minimum amount of knowledge. And then if this knowledge is so complex and then it's not required for doing something, then I won't ignore these complex knowledge. So that actually, yeah, understand? That is the meaning of abstraction. Okay. So that means just ignore the complex thing, just understand the minimum amount of knowledge which is required for doing something. Okay. Okay. Let's take an example like this. So this is the car, and then a kid is driving a car, so that's illegal. But so if we see the car, then we can just see the which part: handle, accelerate, accel, brake, and then some what is this? Is gear. Okay, gear. So we just need to learn how to handle and then how to push the brake pedal and then accelerator pedal. Also how to manage the gear system for driving a car. Right. But inside of this car, the systems are very complex. So we know that the car needs the engine system, also the engine system works with the cylinder, like, and then 4 steps of engine system, engine operation. Also, the gear is connected to the some wheels and then some motor system of this car. But in order to drive this car, we just need to understand how to handle, how to manage the handle, and how to push brake and accelerator pedal, and how to manage gear system. And that's it. We don't need to know about the very complex system of the car, inside of the car. That is the example of abstraction. So in fact, the car system is very complex, but we just, the simple interfaces are just revealed to the user or some customers. So the customers need to understand the minimum amount of knowledge about the car, not the whole knowledge. And then they can use the car very efficiently. That is the abstraction. Okay. That's the example of the abstraction. So another example is the vending machine. So we don't know how the vending machine works. And then actually inside of the vending machine, there is a processor that process some input and output of the customers. But we don't know about everything inside of the vending machine. We just push the button because buttons are interfaces between vending machine and customers. And then only the minimum interface, so minimal interfaces are revealed to the customers because vending machine systems are very complex. But customers do not want to understand that this detailed system of the vending machine. That is the abstraction. So what is the abstraction? Just ignore the complex things and then just understand the minimum amount of knowledge which is required for doing something or learning some systems. That is the definition of abstraction. Why this? Why is this important in computer system? Because computer systems are very actually complex. And then computer systems are composed of many layers and then that is the many components. So this figure shows the various layers of computer systems. So actually in order to learn our computer systems, like smartphone or laptop computers. The computer is composed of actually the electric devices such as CPUs or chips, and then also some I/O devices such as keyboards and mice. So these are all chips, and the inside of the chip there are circuits, and then circuits are composed of transistors, and then and actually each transistor, it works based on the theory of electronics. And then how about the software? So as a customer, we just see the very outer layer of the software, but inside of the software, actually the software is also composed of many layers. So softwares are composed of some interfaces between some library and some outer world. Also, the software includes the very complex libraries, and then under this user application, there is an operating system. So operating system receives the signal from this user applications and then just transfer this signal to the hardware. Also, operating system manages each component of hardware. So actually, if we just focused on the software, so softwares are also complex systems. But we don't think this complex software is, we don't think the software is complex because we just see the outer interface, like some display and then input and output I/O, like a touch screen and the mice and keyboard. So these are also, these are just revealed to the customers. Okay. But inside of the computer systems, there are many layers, and then that means that, and then each layer is also complex system. And then actually it's not easy to understand the detail of each layer. So actually for this course, we just focused on the architecture layer, like this layer. So like instructions and registers. So we will learn about the register of the computer processors. Also, we will learn about the microarchitecture. So microarchitecture is some detailed architecture inside of a computer processor. So actually for this course, we will learn about these two layers, architecture and microarchitecture. And then under this microarchitecture, there are many logic systems. So if you took the digital logic design, COSE222, so digital logic design course. So if you took this course, digital logic design course, then I believe you learned about some logic gates such as AND, adder, multiplier, flip-flop, divider, something like that. So these are the all logic systems. So microarchitecture, like so we learn also about this microarchitecture. Microarchitecture is composed of many logic designs, and then logic designs are composed of digital circuits such as the AND gate, NOT gate, OR gate. So actually these gates are composed of transistors. So actually these knowledges are all required for building entire computer systems. Also, we need to learn about the software part like this. With the software, computer hardware is just a brick. 벽돌이죠, 벽돌. A brick. Okay. but we cannot understand everything under our computer systems because it's too difficult. So and then so it's just too complex, and then the amount of knowledge is also very large. We cannot understand. So we just focus on the specific layers of computer systems, and then also we need to learn about some interfaces between layers like this. So these are the minimum knowledge. So we need to understand how the signals are delivered from the bottom layer to the upper layer. It's the same. So over this architecture layer, there is operating system layers. So that means the architecture layer just delivers some signals or some data to the operating systems. And these are the interface. So we need to learn about the interface between adjacent, that means neighbor layers. Okay. So below your program. So this is also the simplified layers of the computer system. So below your program. So we just see the application because we are customers. So we just see the application software. And then this application software is written in high-level languages such as C, Python, Java, something like that. Also, under the application software, there is system software, like compiler and operating system. And then as a computer engineering students, you will also focus on the compiler and operating systems. I believe the operating systems are also mandatory course in the computer engineering, okay? And then under the system software, there is hardware, like a CPU, memory, and I/O devices, okay? And then let's see how our programs are work. So actually we write the program with the high-level languages such as C and Python, like this. And then I mentioned that the machines cannot understand these high-level languages, right? Because machines can only understand the electric signals, like also digital signals such as 1 and 0. So these high-level languages should be translated into the machine code, okay, like this. And then for this translation, the high-level language is firstly translated into the assembly code, ASM. So this assembly code is composed of very basic instructions which can be understood by computer hardware. So, you may think, this looks like English letters, not 1 and 0. So actually, these assembly instructions are represented with some commands and operands like registers or the address of the data. Okay, so if we see the just assembly code, so we may understand how the code works. And then this assembly code is mapped into the digital signals like 000, 100, like this machine language. So as I mentioned, the computer hardware just understand these machine languages or machine code or digital signals. So actually in the hardware, all signals and then all data is stored and processed with this form of the digital signals like this. But the humans cannot understand these electric signals or digital signals. So the instructions can be represented the assembly instructions like or assembly codes like this. And then also it's very hard to understand this code because this is the very basic instructions which can be executed by computer hardware. So we just write the code with the high-level language. So these high-level languages are understandable to the humans. Then it's easy to learn. So someone do not agree, but it's easy to learn. It's easier than assembly code. And then we just see this form of the software. And then by compiler and assembler, these high-level languages are translated into machine code. Okay. Okay. So I explain how high-level language programs are translated into digital code or machine code, which can be understood by computer hardware. Okay. Okay, let's move on. What is this? So what is this? Okay, CPU, right? So many people say that semiconductor technology is very important, actually, especially for our nation, like South Korea. And then if we mention the semiconductor industry, then we can frequently see the figures like this. so this is the it's called the die, not killed. So it's a die photo of Intel i7. This is the die photo of Intel i7 CPU. So we frequently use the laptop computers, but in the previous generation, we frequently use the desktop computers, and then sometimes we assemble these desktop computers because it's more economic, and then also we can build the more powerful computer systems when we assemble the desktop computers. So assemble means that we just purchase the CPU, RAM, and then mainboard. We just put the CPU on the mainboard, and then put the DRAM DIMMs on the mainboard. So I mentioned a CPU chip. So if you just see the CPU chip, the CPU chip looks like this, okay? This is the CPU chip we can see. And then inside of the CPU chip looks like this. So CPU chip is composed of a large amount of transistors. For example, recent Intel i7 used the more than billion of transistors. So billion is 10억. So it's a very large amount. So this is a dipole. Then there are billions of transistors inside of this processor, this die. And then if we just see this dipole, can you understand how CPU works? No, it's not easy. It's just a sample of transistors, and it's some good looking figure, okay, good looking photo. Just the photo there. So how can we understand the CPU with this photo? So this is this photo just shows which part is which component inside of the Intel i7. So actually it's the same photo, and then on the same photo we just categorize which component includes which area of the entire Intel CPU chip. Okay, so as you can see, oh, this is the CPU core, oh, it's a GPU, it's a system agent or IO control. Oh, this is the memory controller, which is different. It's just a box, but if we just see the box, but we can understand which part is which component of the CPU. It's also some simplified abstraction. So there are so many transistors, so if we cannot focus on each transistor on this photo, but if we just use some rectangle boxes on the photo, then we can understand, oh, this is some part of the CPU. And then if we see this photo, then we can understand that, oh, this chip or this CPU includes how many cores? 4 cores. The CPU cores, 4 cores. And then, oh, this CPU includes the GPU, the integrated GPU. Also, oh, there are 4 cores, and then 4 cores are connected via ring interconnection. And then, oh, memory controller is here. So memory can be connected to this part. That's what we can understand with this photo. Okay, that means this is the abstraction level. So with this abstraction, we can understand some knowledge regarding this i7 CPU. Okay, and then what's this? This is the architectural view of the Intel CPU. Oh, so you can see this CPU core, and then inside of this CPU, you can find the many components inside of each core. So you did not learn about the computer architecture yet, so you can understand these figures actually. But as you can see, if you see this figure, you can find some rectangular components, like, oh, it's a cache. What's this? It's a decode. So instruction fetch. What is EU? It's a scheduler. So another cache, TLB. So you can find many components which is represented using rectangles. And then you can find, oh, each components are connected via arrows. So these arrows represent movement of data or movement of control signals. Okay, this is the another abstraction level of the processor. So this is architectural, microarchitectural view of the Intel CPU or Intel core. So if we see that this figure, then so actually if you study the study about the computer architecture, then you can understand, oh, this part is cache. Oh, this component is a cache. So the instructions are read from the instruction cache, and then instructions are delivered to the instruction fetch engine and decoder, and then instructions are decoded here, and the instructions are issued to the processing engines, and then access the data cache. So, and then signals are connected between components. So, and then actually inside of this component, these components are also composed of many transistors and many logic gates, and then various what's that? It's a circuits. We cannot understand about the details of these circuits, logic gate, or some transistors. But with this figure, we can understand, oh, this component is to something. Oh, the signals are connected between components. So we can understand how CPUs work. So this figure do not show the detailed transistors or detailed circuit of the CPUs, but this figure shows some components and then signals between components inside of the core. Then we can understand how the computer processor works. It's also example of abstraction. What is the detail? Some transistors, circuits, these are the details. The details are hidden to us, but we just study some components and then interfaces, and then some control signals, and then data movement inside of CPUs. So we will learn about these levels inside of computer systems. Okay, these are also another example of abstraction. Okay, do you have any questions? Okay, let's move on. So what is this? What is this? Yeah, right. It's a main board. It's the photo of a main board. So actually, in this figure, we just focus on the CPU. That is the processor chip. It's a processor chip. And then, yeah, so CPU is a very important part of the computer system. It's like a brain in our human body. It's very important. And also it's very complex. You can understand about the details of CPU. But with the single CPU, the computer does not work. So it's not a computer system. So the computer systems are also composed of many other components, including CPUs. Okay. So actually many components are connected via mainboard. It's called the mother. Sometimes it's called the motherboard, or it is also called the mainboard. So this is the CPU socket. So CPUs can be attached to this socket. And then these are the DIMM slots, so memory slots. So we can put the DRAM DIMMs to these slots. And then the CPUs, so actually through the main board, the CPUs are connected to the DRAM. It's a memory, it's a main memory. Also, the CPU, so in the computer system, there are many I/O devices like a keyboard, mice, then a monitor, and then touch screen, something like that. So these I/O devices need to communicate with the CPU because CPU is similar to our brain in our human body. So actually there are many components like hands, feet, and then some other organs inside our human body. But these human bodies are controlled by organs are controlled by our brain. And then the computer systems are similar. Computer system is similar. So that means through the main board, many I/O devices are connected, and then these I/O devices are controlled by CPU, the central processing unit. So that means in the system view, computer system is the assembled components of processors, memory, I/O devices, networks. And then these are also some assembled hardware parts inside of the computer systems. It's also complex. Okay. Actually, in the previous slide, we focused on the inside of the CPU is a processor, but for the entire computer systems are composed of many components like CPU, memory, and graphics. It's like a GPU, graphics processing unit, and then storages like hard disk drives or solid state drive like SSD. So these are some simplified view of the computer systems. So it's some systemical view of the computer systems. So this abstraction level is higher than our previous abstraction level. Now in the previous slide, we just focus on the inside of the CPU. So it's a more detailed abstraction level. But now we just focus on some components inside of the computer system. It's the more systemical view. So computer components are connected like this, but it's some old computer system architecture. So CPUs are connected to memory, like it's a DRAM via memory bus. And then, so actually in the previous computer system, there was a north bridge chip, and then those bridge chips are connected to south bridge chip, and then south bridge chips managed data communications between storage systems and then many other I/O devices. And then CPU and the data movement between CPU and these main memories are controlled by north bridge chip. This is the old view of the computer systems. And recently, this north bridge chip part is integrated in the CPU recently. So actually, the modern computer system is composed of CPU, and then CPU directly control the data movement between DRAM, also data movement between GPUs, because GPU handles a large amount of data, because we recently used the Full HD or even UHD monitors for gaming or TV. That means that each pixel is actually data. So that means the graphics processing unit needs to handle that large amount of data. And then in order to handle this large amount of data in the computer systems, the CPU is directly connected to the GPUs. Also, main memory is also important. So actually every data is stored in the main memory, and then also data is directly handled by CPU. So as I mentioned, in the old generation computer system, there was a node bridge chip, and the node bridge chip controlled the data movement between CPU and memory. But node bridge chip is integrated into the CPU, and then CPU directly control the data between graphics, GPUs, and the RAM. Then this I/O chip is a south bridge chip. It's a mainboard chip. So this I/O devices, network, and storages are connected via this I/O chip. It's a mainboard chip. So this is the another system architectural view of the computer system. Then I brought this figure from the Intel mainboard document. So as you can see, so this is the CPU, and then this is the mainboard chipset, and then you can see which component and then which part is connected to CPU, and which devices and which storage is connected to mainboard chipset. So why do I show this? It's the systemical view, system architectural view of the computer system. It's a more higher level abstraction of the entire computer system. So with this figure, we can understand how each component of the computer systems is connected each other. Okay. With this figure, we can understand how the CPU is connected to memory, GPU, and mainboard chipset, and how other devices like storage, I/O devices are connected to the mainboard chipset, and how the CPU and mainboard chipsets are connected. It's the system architectural view. It's another level of the abstraction. Okay. Do you have any questions? So until now, so I explained about the abstraction of the computer systems, and then some architectural view of the processor, and then system architectural view of the entire computer system. So this is some different level of how we can understand the computer hardware or computer systems. It's a different level, but it's the example. And then with this abstraction level, we just understand some knowledge, so revealed knowledge, but some details are hidden. But it's the required knowledge for studying this computer hardware or computer systems. Okay. Okay. Let's move on. Sorry. Okay. I will briefly explain about some technology under the processor and memory. So this graph shows the capacity of the DRAM. So as you can see, the capacity is increased linearly. Linearly? No. So if you see this graph, you need to focus on the scale of the y-axis. Also, we need to focus on the scale of the x-axis. So what is the x-axis? X-axis represents the year, some time, and then y-axis represents the kilobit. So kilobit, so that means the capacity of the memory. But as you can see, the y-axis scale is the log scale. And then this graph increases linearly. Y-axis is the log scale. So that means the capacity of the memory increases exponentially. That is how the VLSI technology advances until now. So capacity increases exponentially. That means the size of the transistor shrinks year by year. And then when the transistor size shrinks, the density of the chip increases exponentially. So that is the trend of the advances in VLSI technology. And then based on this advanced in VLSI technology, the performance performance of the computer system also increases exponentially. Also, the cost of the computer systems reduce, okay, have reduced. So that is the technology trend, because the computer system hardware technology is based on the advanced in VLSI technology. So that is also very important. So semiconductor industry is the very critical industry all over the world. And then advanced in semiconductor technology lead the advanced of the computer hardware performance. So this table summarized some relative performance per cost of the various components inside of our computer chips. So vacuum tube it's a 진공관. So vacuum tube is invented in about the 1950s, and then relative performance per cost is the 1, and then the transistor is a 35. Then in 2013, the ULIC, sometimes it's called the ULSI, not ultra large scale integrated circuit, So if you see the relative performance per cost, it's very high. It's much higher than the first component, like vacuum tube. So that means actually the VLSI technology advanced exponentially. That means the performance of the computer system also increased exponentially. Okay. And then this slide just briefly show how the chips are made from the silicon. So silicon is actually the element of the sand, SiO4, and then based on the silicon has the property of a semiconductor. It's some half conductor and then half insulator. And then based on the voltage level, this Si silicon can become conductors, or silicon can become insulator. And then based on this property, we can make simple switch on and off with the silicon. So, and then based on silicon, with the silicon cylinder, we just cut the slice of the silicon cylinder, then we just generate the wafers. And then on the wafer, we can just fabricate the transistors, like a CMOS transistors, like here. But if we see the shape of the chip looks like a rectangle, but in this cylinder, the slice of the cylinder is the circle. So actually, in this big circle, we just generate the rectangular die. Is called the die. And then die is the separate chip. And then we just it's called the fabricate. So we just include the package on this die, and then we can manufacture the chip of the electric devices. Okay, it looks like this. So this is the photo of the wafer, and then as you can see, under this wafer, you can find the many dies like this. So this is actually Intel CPU die. And then you can see, this die is part of the die is fabricated under this cylinder. So we can just throw away this incomplete die because we cannot generate the rectangular die on this what is that? This boundary. Okay. So as you can see, on this one circle of wafer, we can just generate some rectangular dies. So we need to just throw away these incomplete dies. And then also there can be some defect on the wafer. And then if defect is found, then this is the broken chip. So we also need to throw away these broken chips. Okay. So this is called the yield. So yield means the percentage of successful dies among the entire possible number of dies. So yield is very also important. So if the yield is high, then the cost of manufacturing this CPUs or processor chip is low, but yield is low. So that means that the successful rate is low. Then the cost for manufacturing CPUs or some various chip is high. Okay, so yield is also important. Okay. For today's class, I will stop here. So in today's class, I explained about the abstraction and the many layers of the computer systems, and then some example of the abstraction is like architectural view of the processor, and then system architectural view of the computer system. And then also I briefly explained about some various technology under these CPU processors. Okay. Okay. Do you have any questions? Okay, good. So wait a second. So can you see my Blackboard here? So in the Blackboard, on the Blackboard, I also posted. So I posted the homework number 0. So this is some introductory homework. So actually the point assigned to this homework is the 0 point. So do not worry about this homework. So this is just the introductory homework. So I made some links under this Blackboard. So you can click the Zoom classroom like this. So you can click the Piazza. So actually the Piazza is important. So on the Piazza, so you can post the questions like by clicking new post here. So if you have any questions or any issues, please post your questions on the Piazza. Okay. Okay. Good. Any questions? Okay, thank you for listening, and then see you on the Wednesday.